Okay, this is example number 2. Example number 2 says determine the intervals of increase and decrease for y equals square root of x times ln x. Now last year, a lot of students had trouble with dealing with these kinds of functions, and so this year I'm making a point to deal with intervals of increase and decrease with different styles of functions. So now here you have a square root function multiplied by a natural log function. The process is very similar, but because you're dealing with the natural log function, you do have to make some considerations. First consideration is a consideration of domain. So if we're looking at the square root function is valid when the inside of the square root is bigger than or equal to 0. Natural log function is valid when the argument of the natural log is positive. So overall, this function is valid when x is bigger than 0. And that's important to keep in mind. So a lot of people will make number lines, and their number lines will kind of go all the way back and forth, all the way from negative infinity up to positive infinity. But that's not quite right here. That's not what we have. What we have is the function is clearly undefined for values equal to 0 or less than 0. And we can exclude those from the domain of the function and also from the domain of the derivative. Okay, so you don't have to worry about negative values or even 0. So I'll just make a line here to indicate that. So this line, this dotted line, x equals 0, symbolizes that 0 is undefined, and anything to the left of that is also undefined. Okay, so we don't need to worry about those values. Okay, let's take the derivative and let's try and figure out where it's positive and where it's negative. Before we take the derivative, actually, I'm going to erase this and then rewrite this a little bit. So here we have to apply product rule. Product rule says take the derivative of the first. So that's just simple power rule times the second plus the first. Okay, times derivative of the second. The derivative of the natural log function is 1 divided by x. Okay. Next, what we're going to do is just simplify. So just copy everything and then simplify this. So if you have half a power of x in the numerator, 1 whole power of x in the denominator, overall you're going to get x to the power of negative 1/2 after you simplify. Now here you have to, this is where a lot of people got stuck last year. You kind of have to put it into factorized form. You have to put it into a form where you're able to tell whether the derivative is positive or negative. And here what that means is pulling out this common factor. So we have a common factor of x to the power of negative 1/2 that we can pull out from both terms. And also we can pull out a half from both terms because a half goes into a half once and a half goes into 1 twice. So if we pull out those common factors, we get 1/2 x to the power of negative 1/2. That's what we're factoring out. After we do the factorization, we get ln x, okay, because this half goes into this half once, this goes into this once, and then you have ln x left over. And then plus, here you got to be careful, 1/2 goes into 1 2 times, and then x to the power of negative 1/2 goes into x to the power of negative 1/2 once. Okay, and so that should be the correct factorization. And then I'm just going to simplify a little bit. Just write it in a form that's a little bit nicer. 2 plus ln x all divided by 2 times the square root of x. And that's just some exponent rules. Okay, now at this stage, you need to look to see where the function's undefined and where it's 0. Well, it's going to be undefined if x is equal to 0. The thing is, though, we've excluded 0 from the domain of the function, so we don't even have to worry about that. So the function, the derivative here, it's never really, at x equals 0 and to the left of 0, it is undefined, but we don't really need to even consider those. Really, you just have to worry about the numerator. See where the numerator is positive or negative, and then just deal with that. And this is where you kind of have to remember things from DP1 when we were talking about the exponents and log units. You need to be able to solve the equation 2 plus ln x equals to 0. And you need to be able to determine, hey, to the left of this and to the right of this 0, what's happening to the function. So here you have to look at the sign, positive or negative, of 2 plus ln x. So let's first figure out where 2 plus ln x is 0. Well, 2 plus ln x is 0 when ln x is negative 2. ln x is negative 2 when x is equal to e to the power of negative 2. It's the same as 1 over e squared. Okay, so at x equals 1 over e squared, we seem to have some situation where our derivative is holding a value of 0. Okay, and what we need to do next is, again, use our sign chart, but we need to look to the left and right of this critical value, this value where the derivative is 0. And here you do have to think a little bit carefully. You first need a value that's smaller than 1 divided by e squared. And you know, one option is to just use a calculator. Without a calculator, though, you have to be a little bit clever in choosing that value. So you could say that 1 over e cubed is smaller than 1 over e squared. The reason we can say that is because the denominator here is clearly larger than the denominator here. And so this fraction as a whole is smaller than this fraction. So if we try 1 over e squared, I'm going to erase all this. If we try and plug in 1 over e squared into ln x, or 2 plus ln x, I should say, 2 plus ln of 1 over e cubed is 2 plus ln of e to the power of negative 3, which is 2 plus negative 3, which is negative 1. Okay, so what I'm saying is if you try a value in between 0 and 1 over e squared, we seem to be getting a negative value out. And similarly, if you try a value to the right of 1 over e squared, and I'll let you think about what values to try. So think about what value could be bigger than 1 over e squared. You will get a positive result out. Okay? So let me just erase everything here. So what we have is our derivative is negative, then positive. And so our original function, I'll just call it y, our original function is decreasing, then increasing. And so we can say, well, it's increasing on the interval from increasing on the interval from 1 over e squared to infinity, okay? Or you could just say larger than 1 over e squared. And here we're going to include 1 over e squared. The reason we do that, again, is because the derivative is 0 there, and the function is well defined. And then it's decreasing on the interval from 0 to 1 over e squared. We're not going to include 0 because the function is undefined there. And we are going to include 1 over e squared. What I encourage you to do is maybe just pause a bit and actually graph this function on your GDC and just confirm that these intervals of increase and decrease hold. It's important to be able to kind of connect the graphical representation to this sign chart.